Hello, and welcome back to part 3 of the Standbridge Pharmaceuticals problem and our discussion of sensitivity, the objective function coefficient ranging, or OFCR ranging, and the optimal schedule. We're still looking at the Standbridge Pharmaceuticals problem, and if you don't remember it very well, you might want to check one of the previous 2 videos to make sure you know what's going on. I'm going to give a real cursory summary right now in terms of how things relate to objective function coefficient ranging. So in particular, we're going to be focusing on what the decision variables are and what the objective is. Because when you're doing objective function coefficient ranging, the numbers that you're changing are these ones here, the numbers in the objective function itself. We're only changing one at a time for now. If you want to change more than one at a time, you need the 100% rule, which is what the next video is about. But as we're standing right now, changing one at a time, we're changing these numbers, and we're asking how far we can change them before some of the numbers in red change too. As long as the numbers in red stay the same, we have the same optimal schedule. We're doing the same stuff. Outside of that range, the optimal schedule is probably going to change. So as an example of how we could do OFCR ranging, we could talk about taking, for example, the pay that a senior chemist gets for regular time work and changing it from $50 to, let's say, $60. Okay? Now you'll notice that this is a negative coefficient here because the objective is profit, and paying the senior chemist is actually giving us a negative profit because it's incurring a cost. If I change this number right now from negative 50 to negative 60, like that, you'll notice that my profit, negative 934, is going to change. It changes to 854. Not surprisingly, I'm paying that chemist more money per hour. He's working 8 hours, and so I'm making less money. But the question is this really the new optimal solution? After all, if I'm paying the senior chemist more money, maybe I want to do something different. Well, let's find out from Solver whether I really do. I'll go into Solver, and I'll say solve. Okay. And as you'll notice, frankly, Solver says, nope, 854 is the best we can do. If the senior chemist gouges us for an extra $10 an hour, there's nothing we can do about it other than simply pay it. But I hope that you see that if the senior chemist got too big for his boots, eventually that would change. Suppose, for example, the senior chemist decided to charge $200 an hour. That means that every hour that the senior chemist works would reduce our profit by $200. Now, if I leave things alone and simply find out the effect of that, my objective is now negative $266. At least it is if I keep my same schedule with the senior chemist working an 8-hour day. But would I? You might think not. Let's see if Excel agrees with you. Running Solver again says, no way. I'm still losing money at $80, but the senior chemist is being used for no more than 6 hours now. Because he costs more money, I've changed my optimal schedule. So what did we just see? If a change in a coefficient is not too big, the optimal schedule stays exactly the way that it was before. But if the change is big enough, we expect a change in the optimal schedule. Let me go back to changing this number back to what it was, negative 50, solving the program again to find the old optimal solution. And if you'll remember, last time I got a sensitivity report for this problem by clicking on the word sensitivity at this point and saying OK. That's what created this sensitivity report tab down here. I'm not going to do it again because I don't need another one, so I'll simply say, I'll get rid of that and say OK. All right, let's take a look at that sensitivity report and see what it has to say to us. Here's the whole report. As you'll recall from last time, it has an upper part and a lower part. The lower part was what we dealt with for right-hand side ranges, which is not today's focus. So I'm going to focus on the upper part of the chart, the part that deals with OFCR ranging, objective function coefficient ranging. How's this part made? Well, the first thing is I'm going to talk to you about this column of reduced cost. You will never, ever use that column. So if I were on a test, I'd probably just cross it out. Today I'm going to gray it out quite a bit because it's not going to be important for our work. For those who are interested, the reduced cost is the negative of the shadow price of the non-negativity constraints in the program. Okay? But you won't need it. All right. What do the other columns mean? Well, first of all, we have the names of each of our variables. Oz made, the number of ounces of chemical which are made, the pharmaceutical tachyon. Remember, they wanted 7 ounces. The total amount of time it takes to make this, we pay a penalty of $30 per hour for every hour it takes to make the chemical. How many regular time hours and overtime hours the senior chemist works, how many regular time and overtime hours the junior chemist works, and how many hours the lab tech works. All right, the numbers in the final value column are telling us the actual optimal values of these variables. So right now we're making 7 ounces of tachyon, the pharmaceutical. We're using 9.2 hours to do it. The senior faculty is working 8 hours of regular time and 1.2 hours of overtime. The junior faculty is working 8 hours of regular time only, and the tech also works 8 hours. These are the same numbers that we saw in the decision variable cells here. These numbers here, 7, 9.28, and so on, are echoed right here, 7, 9.28, and so on. The objective function coefficients are also from the previous page. They tell us how much profit we get from each of these activities. 300, negative 30, negative 50. You can see on the original page, 300, negative 30, negative 50, and so on. Okay, but it's these numbers that we're going to be changing. Now, in an OFCR problem, those numbers will always represent the worth per unit of something, where worth is whatever the objective's measuring. In this problem, the objective's measuring profit. So when you're doing OFCR in this problem, you're changing the profit per unit of something. For example, right now, our chemical, our pharmaceutical, tachyon, is bringing us in $300 an ounce. If it was worth more or less, I'd change that number. All of the rest of the coefficients are negative here because everything else that we have costs us money. Here's our penalty per hour for taking time to make the pharmaceutical. Here's how much we must pay the senior chemist, how much we must pay the junior chemist during regular time and overtime, and finally how much we have to pay the lab tech per hour. Keep in mind these numbers are negative because it's going to have an effect on our analysis too. Okay, let's see how what we just did a little while ago fits in with this. I asked you what would happen if the senior chemist changed his cost per hour from 50 to 60. That would change this coefficient of negative 50 into a coefficient of negative 60. Changing negative 50 to negative 60 is a decrease of 10. Notice that the allowable increase and allowable decrease columns tell me how much I can change these things and still stay inside the range. My allowable decrease is 25. I'm only decreasing it by 10, so I am inside the range. Now, with a right-hand side range, being inside the range means that the shadow prices don't change. But here it's different. Inside the OFC range, or the OFCR, inside the range means the final values don't change. That is, you're still doing the same stuff you're doing before. And this is how we started this lecture. We said that if that negative 50 became a negative 60, we'd keep on doing the exact same thing we were doing before. How would our costs change? Or our profit, I should say? Well, we're making $10 less profit for each one of these 8 hours that guy's working. Our profits are going down by 80 bucks, 8 times 10, because we have an extra $80 cost to pay the extra salary for the senior chemist in regular time. Let's try a different one and see what it has to say. For example, suppose that the penalty that the company was charging us for making this drug, this pharmaceutical, wasn't 30 bucks per hour it took, but was instead, let's say, $37 per hour that it takes. Well, let's make it 40. It's easier to think about. Okay? I'm changing this negative 30 to a negative 40. First question, have I stayed inside the range? Certainly not. Changing negative 30 to negative 40 is decreasing it by 10. A decrease of 10 is forbidden by the allowable decrease of 3.33. Now, when I say forbidden, I don't mean you can't do it. You can. What I mean is, if you change it that much, these numbers over here, these final values, are probably going to change. So I can be more specific. I can say, if you charge me, for example, negative $33, if you charge me $33 per hour, then I'm going to keep the same schedule. But if you charge me $34 per hour, that's 4 less than where I am right now, then probably the schedule will change. Let's give it a try. We're back to the original sheet. Take a look at these numbers because this is the current schedule. I'm going to change the cost per hour from negative 30 to negative 33. Remember, we predicted that all of these numbers would stay the same. Obviously, my profit will change because I have to pay a bigger penalty. In fact, the profit would change to that. But I'm saying that these numbers should stay the same. Let's find out. We'll go over to Data, Solver, Solve. And sure enough, all of those numbers are what they were just a moment ago. But I said that if I make it negative $34, the optimal schedule would change. That's not just the profit that's changing. We're actually going to do different stuff. So that 7, 9.2, 8, 1.2, 808, something different should happen. Let's see. Solver, Solve. And you saw them change, 7, 8.75, and so on. We have a different schedule because we moved outside of the OFCR range. Now, I'll be honest, outside the OFCR range doesn't always mean the schedule will change. It usually does, though. There are some possible cases where being outside the range could still see no change in schedule, but it's very uncommon. Inside the range, however, you're sure that the optimal schedule won't change. So let me put it back to -30, where it was, and go back, resolve the problem, the original problem, and let's talk a little bit more about this. Back to the sensitivity report. Okay, you've got the basic idea of how these things are working, but I do want to talk about what an infinity means when you see it in an allowable increase or an allowable decrease. You see them up here too. That 1 times e to the 30 means 1 times 10 to the 30th, and that's how Excel's telling you infinity. So what this means is that that coefficient can go on forever in that direction and not change the optimal schedule. For example, right now I'm using the senior chemist during regular time for 8 hours. This positive infinity means that if instead of costing $50, he cost less, even if he was paying us to letting him work, we still would only use him for 8 hours. Now, that actually makes sense, because if you look back at the original program, you'll see that there's a constraint that says that the senior chemist, can only work for 8 hours. There's no way he's allowed to work more. So even if he'd pay you to be allowed, you couldn't. Let me generalize this a bit more. Anytime in the OFCR report that you see a variable which goes up to positive infinity for its allowable increase, or down to negative infinity for its allowable decrease, it always means one of two things. Either that variable is as big as it possibly could be in the problem, or it's as small as it possibly could be in the problem. Any more extreme value would become infeasible. For a max, increase means as big as possible, decrease means as small as possible. For a min, it's exactly the opposite way. So this is a max problem. Let's interpret them here. We have plus infinities here and here, for example, and here, which suggests that those variables could not possibly be made any bigger than they currently are. Why bigger? It's a max problem, and we're talking increase. Well, that's true. The customer only wants 7 ounces of this drug, so we can't make any more. We're using all available regular time for the senior chemist. He's not allowed to work more than 8. And the junior chemist, she's already working 8, and that's as much as she's allowed during regular time. These variables could not possibly get physically bigger, and that's why the range goes up to infinity. But we have a couple of negative infinities as well, here and here. For a max problem, that means the variable is as small as it could possibly be. Let's look down here, for example. This is how much overtime the junior chemist is working. Currently, the junior chemist is working 0 hours, and it's impossible for the junior chemist to work less than 0 hours. That's what that negative infinity is doing there. Up here, it's impossible for us to make less than 7 ounces of the chemical, because we have a constraint that says we have to make exactly 7 ounces of tachyon. No more, no less. And that's what the infinities are doing. Okay? Well, that's the basic idea of what's going on with objective function coefficient ranging. If you're trying to change more than one coefficient at a time, you need the 100% rule. There's one more thing to say. If I go all the way to the end of the OFCR range, I'm almost always in a situation where I have alternative optima. Let's take a look at one. For example, the end of the junior regular hours constraint goes down by 13 hours. From -30 going down by 13 means -43. That would suggest to me that if the junior chemist charged $43 per hour during regular time, I'd have 2 different equally good answers. Let's check and see if it's true. Back to the problem. I'll change the junior chemist's cost to -43, meaning she's charging $43 an hour. That's obviously going to change my objective function value. But does it change my optimal schedule? Right now I'm making $830 with the old schedule, but do I want to change it? I'll hit with solver and say solve. My value is 830, and I'm doing exactly what I was just a moment ago. Now let me go looking for a second optimal solution here for these same numbers. To look for one, I'm going to change that 43 to a number that's slightly more negative. It should be outside the range. Let's say -43.01. I'm predicting that we should get a new optimal solution now. And I hit solver. And you can see, yeah, it is. The time here has changed. The total time is now 10 hours. We have a different solution. But if I change that negative 43.01 back to the negative 43 we had a moment ago, I still have $830 profit. That is, I found two different solutions with a cost of $43 per hour of regular time for the junior chemist, and both of them give me the optimal profit of $830. That's the alternative optimal we were talking about just a moment ago. Well, it took a little longer to get there than I wanted, but I hope this gives you some idea about how OFCR ranging is working. In our final video on sensitivity, we'll look at combining different kinds of ranging, if we can, and different numbers of quantities, and see how all the pieces fit together. Come back one more time, and I'll see you then.